In this problem, we're told we're at the equivalence point of the titration of acetic acid with NaOH. So the first thing to do is identify the salt, which we know exists at the equivalence point, and that would be sodium acetate. So since it's the acetate that's going to be reacting with the water, being a conjugate base of a weak acid, we now write the equilibrium for that interaction with water. That will generate acetic acid, and by consequence OH minus. So we want to set up our IREC table. What we need moles of our salt. And the moles of the salt, or moles of acetate, will be equal to the moles of acetic acid that we start with. So we look at our information given above. We find we start with 25 milliliters, or 0.025 liters, at a 0.1 molar concentration. Remember, these are all initial amounts. So we can take that number of moles of acid we started with. We know that's going to be equal to the moles of salt generated. And we put it in our I line of our IREC table. We start with 0 products, so we immediately gain X moles of each product, and we lose X moles of reactant. We now at equilibrium have 0.025 minus X moles of reactant, or acetate, and X moles of each product. We can convert those to concentrations by dividing by the total volume. Remember, the total volume is going to have to include not just the volume of acid you start with, but the volume of base that you let in through the burette. Since we're going to need that, it's not going to cancel out, so we could start by calculating that total volume. We'll need the volume of NaOH, so that will be the moles of NaOH required to reach equivalence point, divided by the molarity, so that's 0.025 liters. Now the total volume would be that volume plus the volume of acid that was initially titrated. We just add those two up. So it's 25 mils of each for a total volume of 50 mils, or 0.050 liters. Now we're set to use our equilibrium expression, Kb, to solve for X, or to solve for OH minus molarity. It's a Kb because it's a base that's dissociating in water, and our evidence of that is the OH minus produced. So the Kb is products over reactant. Since, in this case, those two products are going to be equal in concentration, we can write OH minus squared, molarity of OH minus squared. And then we divide that by the acetate molarity. But it's important that this only works when these two are equal. So we rearrange and isolate OH minus. That'll be equal to Kb times the molarity of the acetate, and the whole square root of that. So for Kb, you can't find that easily, but you can find Ka of the conjugate acid easily. So we'll get Kb by dividing 10 to the minus 14 by the Ka of the conjugate acid. The molarity of the acetate will be the moles of acetate divided by that total volume, which we found to be 50 milliliters. Take the square root of all of that. We can make an approximation, because this is a weak base, that the amount of dissociation will be small, and therefore 0.025 minus X is just equal to 0.025 moles. If we plug that all into our calculator, take the root of all of that, but again, the assumption being that X is much smaller than 0.025, so that 0.025 minus X is equal to 0.0025. So for a molarity of OH minus, we get 5.27 times 10 to the minus 6 moles per liter. This gives a POH. When we take minus the log of this value, this gives a POH of 5.3, and a pH, by subtracting the POH from 14, a pH of 8.7.